In Year 1, we learnt that water molecules arrange themselves in an ordered open lattice structure in ice crystals, with the molecules being fixed in position by the hydrogen bonds. It is important to note that although the water is in a solid state, the molecules still possess energy and are still vibrating, and, like all solid matter, will continue to do so until the temperature falls to absolute zero, that is, a temperature of 0 Kelvin, or minus 273 degrees Celsius. If we increase the temperature, we give the water molecules more energy, and the hydrogen bonds are no longer sufficiently strong to hold the molecules in a fixed position, and they will move freely amongst each other. The hydrogen bonds will continuously form and break, and these bonds help prevent the water molecules escaping from the surface as a gas. If more energy still is added, more molecules possess an energy to completely overcome the hydrogen bonds, and these molecules escape into the air as a gas and disperse. If we had to rank these three states of solid, liquid and gas into levels of disorder, we would obviously put the gaseous state as the most disordered, followed by the water, and have the ice as the most ordered. In chemistry, we can assign numerical values to the level of disorder of substances, and this is called entropy, and is a measure of the dispersal of energy, which is greater the more disordered a system. In the case of the states of water, we can see that the entropy / amount of disorder is dependent on temperature, with an increase in disorder with increasing temperature. Entropy therefore has the units of joule per Kelvin per mole. In nature, systems tend towards increasing their entropy, and the second law of thermodynamics states the entropy of the universe is increasing. For example, when we leave a cup of water out in a room, the water molecules tend to move towards the more disordered state of gas, rather than move back together and fill up the glass with liquid. The entropy value of 1 mole of substance under standard conditions is termed the standard entropy. Just as there are changes in enthalpy in a system during a chemical reaction, there are changes in entropy. Let's consider the thermal decomposition of calcium carbonate to calcium oxide solid and carbon dioxide gas. We can look at the standard entropies for each of the substances involved in a chemistry data book. To work out the standard entropy change, we total up all the standard entropies of the products, multiplying the standard entropy values by their molar amounts in the balanced chemical equation. In this case, there is only 1 mole of each substance, so we multiply the standard entropy values by 1. We do the same for the reactants, and the entropy change is then the sum of the standard entropies of the products subtract the sum of the standard entropies of the reactants. In this case, we see the standard entropy change of reaction is plus 160.5 joules per Kelvin per mole. What this tells us is there has been an increase in the dispersal of energy, which has resulted in a more disordered system. This makes sense when we look at the equation, as we have gone from a single mole of solid substance to 1 mole of gas and 1 mole of solid. As we discussed earlier, gases are more disordered than solids. In fact, just by inspection of the chemical equation, we can sometimes predict whether there's been an increase or decrease in entropy by counting the number of moles of gas on both sides, the side having the greater number of moles of gas having the greatest entropy. In chemical reactions, there can either be an increase in entropy, in which case delta S is positive, or a decrease and delta S is negative.